So first of all, I should begin by saying thank you to David and Angie and Bill for inviting me and helping arrange everything. It's lovely to be here today. So as David said, I work in physics in the Space and Atmospheric Physics group. So what I'm going to talk about is really my main area of research, which is all about space weather. As David said, I also am the director of Space Lab, which is the umbrella network for all of Imperial space activity. So maybe later as well, if you have questions about other things relating to space, I'll do my best to talk about that. So what I really wanted to show you today is tell you a little bit about what space weather is, why it's important, some of the risks that it presents, and why it's difficult to deal with. And then I'm going to, towards the end, talk about what we're doing at Imperial. And so this covers both using computer simulations to forecast space weather and building hardware, so satellite experiments to measure space weather. And so what I'm going to start with is, I hope, movie to talk over. And so when people think of space weather, then one of the things we think about is the Aurora. And so these are time-lapse movies of the Northern Lights. You can click on this link, which I could put in the chat after. And there's amazing photographs of the Aurora. And you can see that it's very vivid and it's very variable. And sometimes you can be very boring and quiescent. And then sometimes it's this amazing dancing display, which has been known about for thousands of years. And yet what actually controls it is a very complicated connection, invisible connection between the sun and the Earth. And so whilst this provides these beautiful displays, it actually has a real impact on our everyday life. And that impact has changed considerably, even in the last 10 years. As our societies become much more technologically advanced, we suddenly find ourselves much more exposed to risks from the physics that controls all of this stuff than we may have been 10, 50, 100 years ago. And so that means that it's a very fast-moving area of research, and I'm going to try and explain a little bit about what that sort of means in practice. So space weather is driven by the sun, essentially. And so if we look at the sun at sunrise or sunset, as shown in this picture, it's kind of a boring, featureless object, and it seems to just hang there. It provides this constant source of illumination for life on Earth. But actually, if we look at it during an eclipse, we start to see that actually the sun is a lot more complicated. And so this is a picture taken on the ground, and when the moon covers the visible disk, it allows us to see the solar atmosphere, and we can see that it has a lot of structure. And this is actually revealing the sun's magnetic field, where the plasma, which is what we can see, the atmosphere of the sun is so hot, it's turned into a plasma. What we're seeing is light, which is associated with this plasma and is guided by the complex magnetic field of the sun. So we start to see that it is more complicated than just a featureless object. But we can only see on the ground an eclipse for a few minutes. And so if we wanted to see this for longer, we have to go into space. And so that then reveals, by making measurements in space of the sun, that actually it's an incredibly complicated and dynamic and perhaps very violent object, creating explosions in different ways. Now, what we're watching here is a movie from a NASA space mission called Solar Dynamics Observatory. We're actually looking at the sun in ultraviolet light, but it's obviously false color, so we can see it. And we're zooming in, looking at just one part of the sun. And so I'll try and show my, well, you can see the main action here happening on the edge of the sun on the limb. And each of these moves is a slightly different wavelength. That tells us slightly different things about the sun because it images slightly different places. You can see these eruptions and brightenings. The brightening is a solar flare. That's an eruption which creates a big flash of light. And then we also have actual eruptions of material. And so the next movie I'm going to show is from a different spacecraft called Stereo. And what we're watching here is an enormous eruption of material lifting off from the sun. And this is called a coronal mass ejection. Now, coronal mass ejections, they travel out through space at maybe 1,000 kilometers a second, and then they take maybe a few days, 2 or 3 days to travel through space, and they go off in all directions. And sometimes the Earth finds itself in the firing line, and sometimes they're ejected and they go off in a completely different direction. So there's really two things that the sun does to create space weather. This, the coronal mass ejection, and the other, which is the solar flare. The solar flare, as I said, is just a big flash of light, travels through space at the speed of light, and of course we only know about it when it arrives. So they each do different things, but actually it's the coronal mass ejections which we particularly concerned about for many space weather impacts. And to try and explain that, I have an animation that was produced by NASA, which is sort of showing some of the elements of this to try and explain what's going on. The coronal mass ejection travels through space, and it, let's say, arrives at the Earth, and it hits the Earth's magnetic field. So as you know, where you're sat right now, there's a magnetic field. And if you were to follow that field out through the room, and it would go out and up into space through the atmosphere, and it creates this protective bubble, which we give the name the magnetosphere. And I'm going to play this again so that you can watch what happens. And that carves a bubble in the flow of material coming from the sun, and it protects us. It provides kind of a shield. And so what you see happening here is that the CME is largely deflected by the Earth's magnetic field, but there's also this peculiar interaction where some of the energy and material from the eruption, the CME, gets trapped inside the magnetosphere and then is released in a complicated process called reconnection. And I'm just going to show the last little bit of the movie again, or try to, sorry, where what happens is material gets, and energy is stored inside the magnetosphere, and it gets drained along the field lines which channel it into the poles. And when that energy, those particles hit the top of the atmosphere, that's what creates the aurora. And that explains kind of why we only see the aurora up near the poles. Now, clearly we understand the basics, but there's many, many parts of the physics in all of this that we don't understand very well. And in particular, we don't really know how to predict when a coronal mass ejection will exactly occur. You can see things brewing, but we cannot say with certainty whether or not a CME will happen tomorrow or 5 days or whenever. And we still don't very well understand the exact process by which some of that energy gets channeled into the Earth's magnetic field and then creates these bright auroral displays and an associated what we call a geomagnetic storm. Now, if I bring this now to the main topic of the talk, so in space weather, what we are thinking about is the concept that just like we have weather here on Earth, as written here, so wind, snow, and rain, there's an entire concept of space weather driven by the sun, which may include solar flares or geomagnetic storms or coronal mass ejections and all these events. And they can impact both on our technology and our activities, both in space, but also on the ground. And there have been a number of reports which are freely available online, more or less technicals, but they do have good executive summaries, if this isn't anything you know about at all, looking at the impact on both infrastructure and other things. And this words are taken from the National Risk Register. And so this is the document which makes excellent bedtime reading because it tells you all the things that terrible things that could happen, which the government is aware of and which the government has a plan or is considering for how to deal with. And you could imagine all sorts of different things appear on the risk register, and severe space weather appears on that register too. I'm going to spend a few minutes just explaining some of the impacts. So this quite busy picture from Bell Laboratories shows all different types of impact space weather can create. So up in space, I think, it's not, it would be terribly controversial to understand, to expect that space weather should affect things like satellites and astronauts in space and so on, because you would get energetic particles coming from these space weather events, and they could cause problems with spacecraft charging or with delicate electronics. But it can also affect the atmosphere and the ionosphere. And so actually what can happen is that you can get disruption to the upper layers of the atmosphere, the ionized ionosphere, and that can interfere with satellite communications. And actually that can not just communications, but also with global positioning systems. And then actually through Maxwell's equations, you have magnetic fields and currents up in space, and they couple to currents on the ground. And one of the real issues that people are trying to get their arms around is that this space weather events can affect conducting systems on the ground and power grids in particular. And so there are events where there have been disruptions to power because of space weather. And we think that if there is a very major space weather event, as could happen 1 in 100 years, it could have quite a severe impact. So space weather is quite different from blue sky research because it's very much led by the challenge. It's not necessarily just exploring blue sky science. It's very interdisciplinary. I think you've maybe got that sense already, but if you really want to understand space weather, you need to involve solar physicists, who understand space physics, who understand rocks and the Earth's magnetic field. But then you also need people who understand spacecraft engineering or power engineering. And then you need people who understand economics and social impact and other things as well. So space weather is a really complicated thing. And it's also made more difficult because we know that events have happened historically, for example, in the mid-1800s, but we've not had such a major event happen during the most modern era in the most recent times. And so impacts are very difficult to also understand. And I did some work on this a few years ago with a consortium I was working with. But you can easily find that if you generate a scenario where you have loss of power over, let's say, Western Europe, you can generate very, very large and scary numbers about what the economic impact might be. Now, these are evidently quite uncertain. And in fact, the real issue is not the size of the event in the first place, because we can't, and indeed we can't control that. It's how long you take to recover. And so a lot of effort is then dedicated to understanding how do you build a resilient system, how do you operate it so that if something happens, you can return to normal as quickly as possible. So in terms of what we're trying to do to better improve our resilience to space weather, there's really two parts to it. One is forecasting, and so trying to have a space weather prediction. And the other is monitoring, and so using satellites to see what is going on. I want to spend a couple of minutes talking about each of those things, and we'll probably discuss that more as we go into the rest of the chat. Because at Imperial, we're working on both sides. So in terms of forecasting, one project that I'm leading at Imperial is doing space weather modeling. Now, earlier on, I showed you an animation about how the space weather chain works. And maybe this movie here then looks reminiscent, because what you're looking at is the side of the Earth's magnetic field. But here, this is a computer model, which was actually produced using the high-performance computing facilities at Imperial. And what we did was to work with our partners in plasma physics. And we took computer codes originally developed for modeling laboratory plasmas, like the MAGPIE experiment, which is in the basement of Blackett. We've adapted them to model the plasma environment of the Earth, which is the Earth's magnetic field in space. And in the last few years, we've steadily built up our capability. And at the moment, we are working on the wonderfully named SWIMMER project, which is a huge UK-wide consortium project trying to transition models developed for research, like this one, Gorgon, into the Met Office and into the Met Office Space Weather Operations Center, the MOSWOC, where they use these to produce space weather forecasts. And so this is a huge £20 million project with partners from across the UK, and is really transforming our ability to understand and predict space weather. And the other thing that we're working on at Imperial is looking at monitoring space weather. And there's a couple of different projects that perhaps we'll talk about a bit more as we go along. And the first one I'm going to talk about is called Lagrange. And so what I'm showing here is that this mission will make use of some really interesting orbital mechanics, which is that between the sun and the Earth, there are special points called Lagrange points, where the gravity of the Earth and the sun conspire, so that if you place an object there, then it will basically sit there as the Earth goes around the sun. So the L1, the first Lagrange point, we put spacecraft there, and then the Earth goes around the sun, and the L1, the spacecraft, basically sits on the line connecting the sun and the Earth. We use that to measure what is coming from the sun. But the other point we want to go to is L5. At this point, you sit and you can watch things going from the sun to the Earth. And you can also peek around the corner and see what's going to be coming around from the side of the sun. And so we're involved in a project called Lagrange, where we'll be building a magnetometer that will sit on this spacecraft and form part of the payload to monitor space weather going from the sun to the Earth. Now, this is a very big project. It takes a long time. We've been working on it for a number of years already, and it's going to be a lot more years until it's really going. And so we're doing another project, which is kind of the complete opposite end of the space hardware spectrum. And so what I'm going to, I will come back to this later, but there's an idea that we also want lots of little satellites. And so we've been working on a project called Rad Cube. And Rad Cube is a CubeSat. And we have built a payload, which is called MAGIC. That's the Magnetometer from Imperial College, which is part of Radcube's payload. And this is a picture, or it's a computer graphic of, I should say, of Radcube. So it's about 30 centimeters long and 10 centimeters on a side. So this is a CubeSat-sized object. And our instrument is a magnetometer, which is highly, highly miniaturized on the end of a little boom. And so the reason I'm mentioning this, and I'll come back to the details in the chat, is because we built our experiment, and this is a picture of it, and this is a 1p coin for scale. So it's very, very tiny, very, very miniaturized, very low mass, very low power. It's really world-leading in its capabilities. And here is an actual photograph of the Radcube CubeSat. And so we were integrated. This was during its tests. And so really the photo that I want to show you, I'll come back to this, but the one I'm most excited about is this photo, because this is the launch of Radcube. And so actually what happened is that Radcube launched just a few weeks ago. It's currently in orbit at the moment and working nominally, and we are sat in the moment before the curtains open, because we're still waiting for our instrument to be switched on. So we're up and waiting and ready to go, and sort of nervously waiting for the command to be sent for our instrument to be turned on and start collecting. So this is a very, very quick overview of the sort of things we're doing. As I've said, space weather is a really, really important area of research, and one in which Imperial plays a really big role. And so what I hope is that we'll be able to talk about it some more. So I'm going to stop this bit and I then bring David in, and hopefully we can carry on from there.
Well, thank you very much, Jonathan. That's, I thought, really exciting, but maybe I've got a special taste there. There are questions already in the chat, I think. So maybe we should start with those. Roger, is there any, I'll read it out, but is there any explanation yet of why the sun's higher atmosphere is so much hotter than its surface?
That is a great question. I should say I can't see the chat at all, so you'll have to tell me what it says. Yes, so the question about why the sun's atmosphere, so the sun's atmosphere is around 1 million degrees Kelvin, and the sun's surface, the photosphere, is a few thousand. And so there's been a long-standing question about why is the atmosphere hotter than the surface, because it seems to violate second law of thermodynamics. And so what we know is that there's some physical process going on to push that, energy through and to heat the atmosphere. There's two competing theories. One is that it's waves, and that there's sort of stirring of the magnetic field and the atmosphere at the surface of the sun, and that sends up waves and that transmits energy, and that heats the atmosphere, the corona. The other idea is this process of magnetic reconnection, where energy is stored in the magnetic field of the plasma, and it gets released into heating the plasma into episodic tiny events. And it's still a very active area of research because we haven't had sufficiently granular data to really see exactly what is going on. And actually, it's one of the real main focus of two new space missions. So one is Parker Solar Probe, and the other is Solar Orbiter. So Parker Solar Probe is from NASA, Solar Orbiter is ESA, and they, between them, are studying the sun close up. And so I expect in the next few years, we'll get a better understanding of which of these processes is more important, or at least under which circumstances does which process tend to dominate.
Yeah, in a sense, at some level, we agree it comes from the magnetic field in some way. It's a question of quite how. We've got a couple more questions. In fact, one of our colleagues, Kelly Stella. Hello, Kelly. He's got a question. Why are long-distance intercontinental fiber optic internet links more susceptible to damage than local links?
So this was, I don't know, yes. So there's a question, it's not so much the fiber optic itself, but it's the repeater stations, I think, that you need to run alongside the fiber optic cable under the sea to power, to boost the signal. And so there's a question, if you've got a long conductor going across the ocean, then in principle it could pick up the geoelectric potential, and then you could get a voltage pushed across the power line that's accompanying the fiber optic. And so there's been debate backwards and forwards about whether or not this would have a significant effect during a space weather event. There was an article in the news a week or two, or maybe this week, which was sort of summarizing a new paper that had been published. And actually this week, there was a big space weather meeting that both David and I were at, virtually or at the Met office. Well, David was there, but this actually came up in conversation of the people at the conference talking about whether or not we thought that the paper was right, basically. And I think the jury's still out a little bit. It's not clear to me that it is or isn't. It could be, but I doubt it's, I'm not sure it's totally apocalyptic.
Yeah, I think actually it's much worse to have a long electrical conductor in the atmosphere, as you get with a power line, or indeed as you get with a railway power system. I mean, there you don't have an intervening semiconductor, that is the sea, which the ocean provides. But certainly, any long conductor under an atmosphere that is undergoing a space weather event is liable to get larger voltages than you expect. And we've been kind of slow to pick up on that. I think we had to have some blackouts in Sweden and in Quebec, in Canada, in North America, before people really started accepting this occurred. Ironically, 50 years ago, in the 70s, a colleague of mine pointed out to the Scottish power authorities that this could occur to, particularly because Scotland is much closer to the Aurora than England. And they said, oh no, not a problem. In 2013, they analyzed data over a very long time and found, sure enough, their systems were getting damaged. Statistically, they found out, according to space weather, the worse the space weather was, the more likely a transformer was to sustain some burnout. Sorry, I think we've also got somebody else asking about this. Oh no, it's Andrew Larkins, who I know knows a lot about this, but he's asking about space weather impacting satellite navigation. Would you like to comment about that, Jonathan? We all use it now. That's how we find our way around the streets, even.
Exactly. And so, like I put in my second bullet point here, when did you last use an actual map? I've talked about space weather with the public for quite a while now, but even in, let's say, 10 years, the way in which I've had to talk about it has changed, because now, let's say 10 years ago, some people would have, who had a phone that didn't have Google Maps on it, before the rise of iPhones. Whereas now, it's just ubiquitous. And so the tricky thing, though, is it's the second level thing. It's not just that you use navigation to find your way around, but those services are tremendously useful for many, many other applications, because it's apparently ubiquitous and reliable and easily accessible. And so I think I would say what needs extra study is really understanding where those other things lie, because people might be using those services without knowing about this potential problem. And therefore, this is what, if anyone say, what keeps you up at night about space weather, it's not the things that we know about, but it's the things we don't know. It's the black swan event, which after the event was totally obvious, but we can't join the dots. And that's partly because it's just so complicated. And in a major event, it would actually be quite complicated. Let's say different coronal mass ejections, different flare, a whole sequence of events over perhaps a couple of weeks. And you could easily imagine that different systems will be impacted in different ways. And so positioning is particularly one that has caught a lot of attention. Power definitely was the first one, because it was very obvious that if there's a risk of losing power over a region, even for a short time, that would have tremendous impact. But with the rise of positioning, I think this one is now coming into view as actually a really difficult problem. And so there's a lot of research into it. And then, of course, as we know, there's a lot of potential impacts in transport, in driverless cars, in 5G, and all sorts of other things where it could have an impact. And that is also driving an enormous amount of interest in space weather at the moment.
Yeah, so there's a very good question from Brian Hogan. It's a bit of a challenge to you, Jonathan. You sit back, you describe CME hitting the Earth as a once-in-a-100-year event. which is concerning given that the last one was 150 years ago. How is the likely frequency estimated?
So yeah, I was what I should say. So CMEs happen regularly, and they occur on a distribution of speeds and sizes. So it's not unusual. For example, at the moment, you might see a CME, and it varies with the solar cycle. So with the 11-year period of the sun during the sort of solar maximum period, you might expect to see a few a day. At solar minimum, maybe a few a week. So we do see them all the time of different levels of severity. So you can imagine a distribution where you have many small ones and very few really big ones. And what we know is that on that distribution, the likelihood of a major event is of the order of 1 in 100. And there's still a lot of debates on looking at the statistics about, is it 1 in 100, is it 1 in 50, is it 1 in 250, and so there is an error bar associated with it, basically. And the way to really look at that is to try and extend back our observations as far as possible. And obviously, we can't go back in the space age, more than a few decades. So after that, there's actually quite an active area of research looking back into proxies and other information to try and figure out the activity of the sun on longer scales and get a better error bar on that kind of. Does that make sense?
Well, it does to me. I imagine it's. I think it is this question of the extremity of the event. I mean, in 1859, which I guess is the famous one, you really had the aurora occurring in the Caribbean, in Bombay, in India, Mumbai. And in fact, you didn't have the aurora occurring probably in the places it normally occurs. In fact, one thing that perhaps people are aware of is how often we get the aurora in England. Well, we don't know because we have clouds so often. But, in the northern end of the British Isles in Lerwick, it's probably every 3 days that you will have an auroral display. The poor population of Lerwick can't see it because normally they're covered with cloud also. But
I have to explain this when I give. It's like, do you see the aurora? And I say, well, I live in South London, so I've got about 15 million people making light. Just even if there was a major event, I'm still not sure to see it.
Yeah, we do get. I mean, we get aurora at our latitudes in London. Probably a couple of times a year, maybe slightly more frequency. But you don't have to go very far north. You get to northern England, it's a moderately common occurrence. That is, it will occur.
Actually, if people are interested, there is a service by Lancaster University called Aurora Watch, and you can sign up on their website, and they will send you an email or a message if there's a likely chance of seeing it.
I recommend that. I mean, it is a moderately reliable service, but it also helps to be in Lancaster or to the north of Lancaster. But yes, so there is, if you try and imagine what on earth had happened to the Earth's magnetosphere, it more or less been peeled away when during the 1859 event, and I have a feeling that is very hard to believe. It had very dramatic effect on things like the telegraph, which wouldn't function because that was the one thing that used long electrical conducting wires at the time. But of course, the world was nowhere near as connected. They didn't have even really electrical power in any serious way in 1859. So we don't know really. We can imagine the impact. Moreover, the impact hits things you haven't thought about. I mean, I found out about this really from drilling for oil in the North Sea, and you discover that drill bits are navigated with the Earth's magnetic field. So if we open the Cambo field, the new field that's being planned, that's right under the Aurora. If you look where it is, north of the Shetlands. So you need to make sure you know what's going on, or your drill bit isn't going in the direction you think it is. Anyhow, some more questions. Okay, so there is something from Friends Events. We will be hosting a talk on Aurora with Melanie Windridge, and we'll publish the details soon. So that's something you can keep your eyes on. Yes, in fact, Andrew Larkins has put the Aurora Watch link on the chat. Any more questions by chat or by raising your hand? Or now I can see some of you, most of you, I guess. Any more questions? It looks like you're speaking, Alan. Can you unmute?
I have, yes. I was asking whether or not the internet could be destroyed.
Oh, right. Good question. That would put an end to Friends of Imperial College until we can meet in person. Perhaps that's a good reason to start meeting in person. Avoid the solar weather threat.
Yeah, I think.
Jonathan.
I mean, I don't know. I mean, I don't think we'd be sort of a apocalyptic due to Stone Age sort of scenario, but I do remember, there are questions about what is so like data centers, routers, connections, fiber optic cables, and so on and so forth. And so are there elements of the global structure of communication structure which are less resilient? And so then I suppose there is a question that if those bits were affected, could that have an impact? I don't think there's sort of a global thing, but one could imagine the loss of data at certain places, or a lack of connectivity for a short period of time, or stuff like that. My feeling is that actually that question has not really been looked at in enormous detail. And it sort of comes back to the issue that I mentioned when I was talking, which is that space weather is so interdisciplinary that to try and answer that question, you need to be able to get in the same room, virtually or whatever now, people who understand the science, people who understand the engineering, people who understand the computing, and be able to communicate in a way that they can use the same language to understand what's going on. And so that's what makes it difficult, and also a bit certainly challenging. So I don't think it would completely destroy the internet, but I think there could be impacts, and I think it would be prudent to put that on the list of things that people should try and explore, basically.
It seems like the sort of thing you ought to be able to say, oh, something going on here, let's disconnect stuff and go into sort of recovery mode.
Exactly. And so one of the things I think is really important is for companies in general to be aware of the issue, to know where to go to get space weather information. So for example, the Met Office here in the UK. Because if you go and say, I run a internet company.
In fact, that's what's rather neat in the UK. At least we've got a single point of contact. In other countries, there's this fair amount of dispute over who's in charge of space weather operations. And happily in this country, the Met Office has stepped up and picked up the ball and is running with it. So they would be the people who would be responsible for proposing mitigations if that's what's needed. So there's an interesting thing from Mike Toombs. On Unst, north of Lerwick, in 1958 for a year, and never saw the aurora. Well, the problem there is that half the year is summer, and it's kind of hard to see. The nights get rather short. But I imagine that clouds were as much of the problem. But that was in 1958. The whole world was looking at the aurora because it was the end of the International Geophysical Year. And there was a lot of auroral observation at that time. Okay, there's a good question from Richard Balford.
Yes.
So
that's a really good question.
Go ahead, Jonathan.
So the no, I think is the short answer. So Earth's moon, how can I put it easily? So basically the moon spends most of its time outside of the magnetosphere, outside of the protective influence of the Earth's magnetic field. And actually for about 3 days a month, it just travels through the tail, and then it goes back out and is exposed in the solar wind. And so what that means is that if you are on the surface of the moon, you are basically going to see everything coming from the sun directly. And the real challenge there is actually with the coronal mass ejections and solar flares, they can create very, very energetic particles, protons and electrons. And normally, though, the magnetic field of the Earth will channel them away or to the poles, or they can't get in to low Earth orbit where the space station is really very easily. But if you're out in the solar wind, you're directly exposed. And so that means that I think you really do need to have space weather forecasts for lunar exploration. And indeed, this happened during the Apollo era. And there's a really interesting slide that shows actually that the biggest of these sort of energetic particle events occurred in between, I think, the last 2 Apollo missions. I think they knew when they launched the Apollo missions each time that the likelihood of activity was low, but these things are kind of inherently unpredictable. So it's always probabilistic forecasts. And there's been an enormous amount of debate about what would have happened if the astronauts had been on the surface of the moon doing an EVA if a major event happened and they were only protected by their spacesuits. And I don't think the answer is completely clear, but it wouldn't have been good, I think, is the bottom line. And so that means that in the ARTEMIS program, and going back to the moon, as is planned now, there's an awful lot of thought going into how to mitigate this risk. And actually, one project that a brand new project we're involved in, is that we've been asked to be part of a space weather payload, which will be on the Gateway space station. And the goal is to provide data that would be used as part of the overall system that would be, giving situational awareness to this issue. So, it's a really big, it is an important question. And equally, when people talk about going to Mars, it is very difficult technically to do that with rockets and everything else. But I think the real question is, it takes a long time to go there. And how do you do that being safely protected from the ravages of everything the sun can produce? So.
Okay, there's another interesting statement from Brian Hogan. The Internet Protocol, TCP/IP, was designed to be bomb-proof, including magnetic pulse. So providing the hardware survives, the Internet should self-heal. Mm-hmm. Of course, the hardware surviving is an interesting question. Moreover, it's an electromagnetic pulse you have to be able to survive. Particularly, you will get radiation, as well as the electromagnetic disturbance. And the radiation can really penetrate into your electronics and possibly take out the electronics and certainly confuse it, creating disruption to the logic and so on. Anyhow, thank you very much, Brian. Do you want to make any comment? I think we'll. Where is? Okay.
I mean, I think, yeah, I have to hold my hands, of course, and say that actually I know nothing about the technology of the internet, although I use it, we'll use it all the time. So it's actually something, because it did come, as I said, it came up at the meeting this week. It's not really anything I thought of very much before. And I'd heard it mentioned, I was actually talking to a colleague who works in solid state physics at Imperial, and I was asking one day, so, what do you think about space weather and fiber optics? And realizing actually it was the fact that you need repeaters to keep boosting the signal that could have an impact. But it's there's a definite research project in it. I think could make an excellent student project actually. So
yeah.
Take that away.
Keeping it under the ocean is a good idea. Okay, there's Roger. Roger, you want to ask a question out loud? I can see you and can unmute you if you wish. You unmute yourself.
I think we both crossed there. I was unmuting myself who got muted again. Yes, I'm wondering if you can tell us a little bit better indication of how fast these solar ejections occur. How fast are they? Are they fast enough, for instance, to escape the solar system? If not, then presumably they are in orbit around the sun. Or where do you find them? It's
no, they do. They do escape. Yes. So what I didn't say was that because the sun's atmosphere is so hot, and at that point the sun's gravity is relatively weak, it means that you can imagine the sun's atmosphere boils off into space continuously. And it forms a supersonic flow called the solar wind, which then flows out through the solar system and well beyond Pluto. And that actually forms another bubble called the heliosphere. So we are bathed in this solar wind flow all the time. And then these coronal mass ejections come out as well, going faster than the solar wind. So at Earth, the solar wind speed is hundreds of kilometers a second. The CMEs could be going 1,000 kilometers a second. And so they go out as well, and they travel out through the solar system. And we know with other spacecraft, so I mentioned Cassini, which David does fondly remember at Saturn, you could measure the impact of a coronal mass ejection hitting Saturn's magnetic field, Saturn's magnetosphere, and seeing the consequences of that. And Voyagers detect them way out in the deep solar system. So they go out and they travel out. And actually where they go in the end, I don't know. I know they go out. Eventually they must reach the edge of the heliosphere, the heliopause.
Yeah, they will end up in intergalactic,
yeah, but whether they can
stars, I mean, it's in the galaxy, but
yeah. Whether they hit the heliopause and dissipate or reconnect or punch, I don't know.
Well, the heliopause certainly has reconnection going on it. So. Yeah. Okay, well, there's a really reassuring statement here that perhaps we should stop worrying about losing the internet, because by the time we have the event, the data centers hosting websites will be flooded with rising sea levels before any other disaster hits. Yes, thank you very much, Friends Events. I won't reveal your real name, but...
Well, if I can put in a word of defense for space weather, so there is an interesting issue. I came back before about positioning. It's also related to communications. And so there's an issue. There was a hurricane, now I've completely forgotten the name, a few years ago in Haiti, I believe. And actually there was an issue with coordinating disaster response because there was problems with communications because of space weather events happening at the same time. I must admit, I can't remember all the details, but it's definitely known as, and other things as well, where it's been necessary to have, ultra reliable communications being affected and so interfering with operations.
Okay, have I caught all of the questions from a very useful collection of questions? Thank you very much, everybody who's asked. I think I've given everybody the floor that wanted it. I'd like to thank Jonathan once again for, I think, a discussion that has clearly got us all thinking, and for a presentation that I thought was very good, very clear. And thank you, Jonathan. I think if people do want to unmute themselves, please do. Then you can.
Thank you very much. It's really great.
I mean, it really was a great performance, Jonathan, and I think some of us have learned something. I at least found out one or two things I didn't know. That's great.
Okay, it's a real pleasure. Thank you so much.
As for the rest, this is the end of the summer, maybe, but it's the beginning of our year. I think we will continue with the large-scale lectures. Will start again in the first week of October, if I remember correctly. And I think our first lecture is on James Webb Space Telescope. I'm afraid the launch date has shifted from Halloween to now, I think, about the 15th of December. But I still feel that I'm closer to the launch of James Webb Space Telescope than I ever have been. We'll see if that comes to pass. And we have Imperial College graduate who built the infrared instrument for the focal plane of James Webb talking to us on Bill, can you remind me of the date? I should have it in front of me.
Sorry, I'll have to look it up, but it's published on the website.
Let's cut to the chase. If you go onto the website, you will see the program up to the beginning of the new year. And since you all are members, there is possibly going to be the possibility of some face-to-face opportunities to meet in the coming months, in the quite close time, I think, possibly, Bill. Mm-hmm. But I think that's still a TBC to be confirmed. But keep your eyes on the website. And personally, I can't wait to meet you all really face to face again. I think it'll be great once we get back together again. But the large
David,
sorry,
David, we have the James Webb on the 7th of October.
Okay, I said it.
Virtual.
Yeah, it said it was the first week. It's Professor Gillian Wright from the Astronomy Technology Centre in Edinburgh, but who is an ex-Imperial person and a good friend of mine, in fact. And she'll be talking about the James Webb, which is just a wonderful story. And I just hope to see it launched in my lifetime. But okay, so the October the 7th, I trust to see you all. And watch the website for other opportunities to come to our Zoom meetings, but also potentially one day to meet face-to-face as members of the organization. Okay, I think I'll bid you farewell there and look forward to seeing you on October the 7th, if not before. Thank you once again.